So I have a sequence of numbers here, 3, 6, 12, 24, 48. And I've been asked to find the value of the 28th term in that sequence based on just the first 5. So if you look at it, we've got term 1 there is 3. Term 2 is 6. Now I want to write that as term 1 with something done to it, because there has to be a pattern for how we're generating these numbers. So I have to sort of figure that out. So how do you get to 6 from 3? Well, you might call that the first term plus 3. That would make it an arithmetic sequence. Well, if we try that pattern on here, term 3 should be 12. So I'd need if this was an arithmetic sequence, it would be the initial term plus the increase again. No, that's not right. This does not add up to 12. So this can't be an arithmetic sequence because I'm not jumping by the same time, by the same amount every time. You'll see that out here, right? I jump by 3, then by 6, then by 12. Well, that's kind of interesting, right? Jump by 3, jump by 6, jump by 12, right? Something funny is happening there because I'm just repeating these numbers again. So I'm going to try a different method of getting to 6. Instead of doing an addition, I'm going to try a multiplication, because 6 is 3 times 2. Now, if I repeat that pattern again, the next term should be the term I had before with this done to it a second time. So 3 times 2 would be 6, times 2 is 12. That's working. Let's try it on the next term. 24. So it has to be the full term I had last time with this operation carried out an additional time. So 3 times 2 would be 6, times 2 would be 12, times 2 would be 24. It's working here. And just to nail it home, 48 should be 3 times 2. And I don't want to write this out so many times. I'm just going to abbreviate that as 4. So if you try that, 2 times 2 is 4, times 2 is 8, times 2 is 16, and 16 times 3 is 48. So I've got this working here. I want to do this to all these terms, because if I do, I might be able to build a formula so that I don't have to calculate all this manually. So 48 was 3 times 2 to the 4. This was 3 times 2 cubed. This is 3 times 2 squared. This is 3 times 2 to the 1. And this little fellow here, I don't see a 2 in that row, but I can write that as 2 to the power 0 because there are none of them. So it's looking like net. I have this number here showing up in every single line. That was my first term. And in arithmetic series and sequence, you called that A, right? The first term. I'm just going to park that in there. Then I've got 2's showing up because these terms are doubling each time. So I'm going to need a letter in there. And I can't use D because D was difference. And the difference in between these terms is not 2. Right? If it were, it would go 3, 5, 7, 9, 11. This number here is the ratio between the next term and the term that came before it. So, for example, if you pick this term and this term, 48 divided by 24 gives you 2. If you pick this term and this term, 12 divided by 6 is 2. That will happen with any two terms that you pick that are back to back. So I'm going to use an R here for ratio. Now, over on this end, that's my term number. And like the arithmetic sequence, do you notice that when this is 5, that's 4. When this is 4, that's 3. When that's 3, this is 2. This is always one less than that number. So I park that in here, like so. So what I've built for you then is the general term for a geometric sequence. So if I want to find term 28, in goes the 28 for n. I need the value of my first term, which is 3. I need the ratio in this particular sequence, which happens to be 2. And then 28 goes in for my n. So term 28 should be 3 times 2 to the 27. And if you have any number sense at all, you're a little excited to see what 2 to the 27 is, because it's going to be a monstrously large number. Let's see. 2 to the exponent 27 gives me 134,217,728. One, 3, 4, 2, 1, 7, 7, 2, 8. And if I triple that, if it wasn't big enough already, 402653184. No, I'm wearing a black shirt today. You may actually be able to read that. 402,653,184. So keep in mind that that's term 28. So I mean, if I started the sequence, right, 3, 6, 12, 24, the 28th term is probably going to land there. So it started at 3, and by the time I got to here, I'm already at 500 million. These things grow very quickly. Now this doubling pattern, right, things that double, well, that's every population chart you'll ever do, right? Bacteria colonies double in size. Human populations double in size every so often. So it doesn't take many generations for 3 individuals to turn out to 500 million people. Okay. I'm going to clean this off, and we're going to try a few examples where different information has been provided. Okay, so you have a geometric sequence where the first term is 4, and the 7th term is 2,916. All right, well, this thing here, term 1 is your A value, so it's going to go in for A. I'm going to start writing that. Tn will be 4 r to the n minus 1. Now I happen to know that the 7th term in the sequence is 2,916. So term 7 is 2916, which is 4 times r to the 7 minus 1. Okay, I can do 7 subtract 1 there. It's 4r to the 6. I can divide both sides by 4. So 2916 divided by 4 gives me 729. Now I have to break an exponent 6. If this was an exponent 2, we call that r squared, and you would break an r squared by squaring the other side. If I have r to the 6, I still need to square root on the other side, but it's not a square root, it's a sixth root now. So in it goes. Now, an alternative notation for square root, you might also see it written as 729 to the 1/6. And that holds up according to exponent laws if you want to check that out, or just try typing into your calculator. That way you should end up with the same answer as using the sixth root. So I have to find the generic root on my calculator. Sixth root of 729 gives me 3. All right, so for this sequence, the general term is the a value, 4, and it's tripling every time. So if I'm trying to get term 10, in goes the 10, equals 4 times 3 to the exponent 9, which is 4 multiplied by, goodness, 19,683, making the 10th term 78,732. So given the first term and some other term, you can start setting up the general term with your a value. Park in the n because you know that for one particular term, and then use that to deduce the r value. So I have a sequence where the first term is 3, and then each term increases by 10% each time until it reaches 4.83153. So I've got my a value here, and my r value is coded in this, right? The r value would be keep what you had, 100%, and increase it by 10%. So that means that each term is 110% of the term that came before it. Now this slippery little symbol there has always meant divide by 100. So if I do that, 110 divided by 100, my r value ends up being 1.10. You can keep that 0 at the end or dump it, it's up to you. I like to leave it there because you can see the 10% sitting there. All right, so my general term then would be a multiplied by the r value some number of times. Okay, now I know eventually this sequence reaches 4.83153. So that's the value of a term. What I don't know is how many terms I'm going to have to apply this in order to get that number. Now you could, if you want, do this manually. Take 3 and multiply by 1.10 times 1.10 times 1.10 until you get to this value. You can do that. If you want to use algebra to go straight to the answer, you're going to need to use a thing called logarithms. So let's give this a try. First off, I have a 3 to clear out of there, so divide both sides by 3. .83153 divided by 3 gives me 1.61051. All right, now I have an exponential here that I have to break, where the variable is in the exponent, not down here in the main line. So I need the antifunction for breaking an exponential, which is the logarithm family. So I'm going to choose to use log base 10, just no particular reason. I just have a button for that on my calculator. So log base 10, 1.61051 is log of 1.10 to the n minus 1. Now, one of the fancy properties of logarithms is it allows you to pop this exponent down in front. And that's just a number. So I'm going to divide both sides by this thing. All right, now you could have in this line or in this line actually typed in log 1.61051 into your calculator and written it as a decimal. And you could have done log of 1.10 here and written it as a decimal, and then taken this heinous decimal and divided it by that heinous decimal to get an answer. If you do that, you will have introduced a rounding error. So if you can just sort of swallow the anxiety deep down that you're going to be dividing by some function and put it over there and do it all at once, your calculator should give you an exact value. So I'm going to type log 1.61051 equals divided by log 1.10 equals, and I end up with precisely 5. No, I'm not quite done. I have to add this one away to get the n by itself. So 5 plus 1 is 6. Okay. The fifth term in this geometric sequence is 768, and the 12th term is 6. Determine the 8th term in the sequence. That's a touch problematic because I don't have any of the A or R information, but never fear. I'm going to fill this information into my general term. So T5 is 768 with an initial term I don't know, a ratio I'm not sure about, but n in this case would be 5 minus 1 gives me 4. Okay. Term 12 is 6 with an A value I'm unsure of, an R value I don't know, but I do know the term number is 12, so this would be 12 minus 1 is 11. Okay, so I'm just going to put a little line here. We did this with arithmetic sequences when you had no A or R value and you subtracted one from the other in order to get the A to cancel out. So you only had the D left to solve for. Well, in this case, subtracting is not going to help because it's not addition you're trying to break between these two things. Here you're trying to break multiplication. So to break a multiplication, you've got to divide one line by the other. So I'm going to take 768 divided by 6, and I'm going to take A r to the 4 over A r to the 11. Now 768 divided by 6 gives me 128. The A's will divide each other out, and I'm left with 4 r's on top and 11 r's in the bottom. Now, one of these r's divides one of those, another one divides, another one divides, another one divides, and that leaves 1 on top, and r to the 7 in the bottom. Okay, so I see a thing here to the exponent 7, so I am going to apply the 7th root to the other side. And if I find my generic root, 7th root of 128, I get 2. Now, that's not r, that's 1 over r. So I have two options here. I can flip both sides, or I can pop the r up there and then divide both sides by 2. Or third, I guess, I could apply the exponent -1 to both sides of this. Any of them is going to work out. I like the flip both sides method. It's really straightforward. So if this was on top, now it's in the bottom. This was in top, now it's in bottom. You don't need to write divide by 1. It doesn't change the value of things. So my ratio between each of these terms has to be cut in half. All right, that gives us a general term then. Oh, not yet. I need my a value. Okay, so I'm going to pick either this or this. Which one you want? Which one you want? Let's go with that one, just because the exponent's smaller. So 768 equals a times 1/2 to the power 4. So 1/2 to the power 4 is going to be 1 over 16. I break division by 16 by multiplying the other side by the same number. And 768 times 16 gives me 12,288. All right, so now I have enough information to get my general term, Tn. The first term is 12,288. My ratio is 1/2 to the n minus 1. I was asked to find term 8 in this sequence. 8 is 1/2, 8, subtract 1. Term 8 will be 12,288, and it's 1/2 to the exponent 7. And 1/2 to the exponent 7 should be 1 over 128. And 12,288 divided by 128 gives me 96. So given these two terms and knowing that it's a geometric sequence, I was able to deduce what a and r have to be in order to make this work. And then from there, I was able to fill into the general term of a geometric sequence in order to find the value of any term based on what those two are. So that's basically it for this. We've seen how to construct the general term from an actual list of numbers. You've seen how to deduce the a value, how to deduce the r value, and how to deduce both a, r, and n if you are given the other information. So I think that's it for this topic, and you're good to go for the practice problems.